Hi everyone, how are you doing? So today we are going to solve few questions, not just few, I mean many questions on sliding window protocols, okay? And also like one or two new concepts we need to see, which are like efficiency and throughput in sliding window protocol, okay? So let's get started. Yeah, so let's start with this question. This question I have taken from Cross, okay, at page number 293. I think this is the 6th edition, okay, Cross 6th edition. Now let's see this question. This question is P24 question. I mean, that's how they are numbering this question. So let's just see this question. Answer true or false in the following questions. Okay. So with SR protocol, it is possible for a sender to receive an ACK for a packet that fall outside the current window. So with selective repeat protocol, is it possible to receive an ACK that fall outside the current window? So if you remember, then what was the selective repeat protocol? So let me just explain you what was the selective repeat protocol. I mean, let me just remind you and let's just solve this question thereafter. So this option is A saying that suppose you are using selective repeat protocol, which means the sender is having some window and receiver is also having the same window. I mean, the length of the window is same or the size of the window is same. So what is the size of the window here? The size of the window is 1, 2, 3, 4. Then it will be also 1, 2, 3, 4. Now, I mean, sender will be sending some packets. Let's suppose the packet number could be anything. Let's suppose 5, 6, 7, 8. Okay, these packets sender is sending. So it is also waiting for suppose 5, 6, 7, 8. Right? The moment 5 is received, so you will be sending 5, 6, 7, and 8. The moment 5 is received, you will say okay. I mean, receiver will say okay, 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 right? And it will send individual acknowledgement. I mean, it will say ACK 5, it will say ACK 6, and so on, right? Okay. Now they are saying it is possible for a sender to receive ACK for a packet that fall outside the current window, which means can it receive a ACK? Can it receive an ACK for something like a like I mean 3 or 4 or maybe something like 9, 10 or something like that? So first of all, for 9 and 10, I mean I don't think that ACK is even possible, but can it receive the ACK for 3? See, don't worry about the delayed ACK and these things, which means that, okay, 3 ACK, I mean, it must have sent before, now it is reaching the 3 ACK. Don't worry about the delayed ACK. The reason being is that I told you the delayed ACK or the delayed data. If this is the case, then the protocol itself won't work, right? I mean, for example, let's suppose that you are sending some packets, okay? Let's suppose 0, 1, 2, and 3. Let's suppose you are sending some packets, right? And now in this case, suppose that receiver is also sending ACK 0. And here at the sender window, you are having 0. I mean, you're sending 0, 1, 2, and 3. And suppose receiver is also sending the ACKs for 0, ACK for 1, ACK for 2, and ACK for 3. Now, suppose for some reason ACK for 1 is getting delayed too much, okay, and every other ACK has been reached. So this is reached, this is reached, this is reached. If these 3 ACK are reached, and if this ACK is not reached, maybe because it is delayed or maybe because it is lost. So suppose that in this case, I'm saying that it is delayed, right? Now, can you tell me that what will sender do? Sender will just retransmit this packet number 1 again, right? So it will retransmit. And you will be sending, maybe you will be saying that, okay, I mean, this has been received. So by some reason you will say that, okay, I mean, you might again send this ACK1. That is fine, right? I mean, just to let the sender know that, see, I have received this packet number 1 again. I mean, you can just send the ACK1. Okay, I mean, just to make sure that, okay, sender also get to know that this packet 1 has been received. Okay, but now suppose that somehow this ACK1 was delayed too much, and now you are sending, let's suppose you are sending, after that you are sending 4, 5, 6, 7, and then again you are sending 0, 1, 2, and 3. Now this ACK1 is delayed too much, and this ACK1 is basically matching with this one. Let's suppose, I mean, it is delayed too much, and then the sender will get to know okay, this AC1 has been reached, and it will think that this is one for this particular packet, right? Are you getting my point? So this sender will think that, okay, this one is for this particular packet, isn't it? See, this one, this ACK1 is for which packet? This packet, right? But it was delayed. So it delayed too much that, okay, even after sending 4, 5, 6, 7, now whenever you are sending again 0, 1, 2, 3, and now let's suppose this one, whenever you are sending again, I mean, you send this 4, 5, 6, 7, and now whenever you send again this 0, 1, 2, 3, let's suppose this one get lost, okay, and but you receive the ACK, this one get lost, but this ACK has been delayed too much, and that is why you are receiving this ACK. See, we discussed this delayed ACK and these things earlier also. So tell me here, will sender ever get to know that one is lost? 0, 1, 2, 3. Okay, so by luck or by unfortunate or by fortunate, this particular ACK has been reached at the moment where sender is also waiting for the ACK1, right? So in this case, sender will think that, okay, this has been reached and this has never been reached, right? So this kind of protocol, I mean, this protocol won't work if the ACK is delayed too much. You getting my point? So how to solve this problem? Anyone remember? I told one line to solve these kind of problems, that we will look in TCP, right? Later in TCP, we will see that how to solve. Okay. So delayed ACK here we are not going to deal. I mean, I will tell you that how we can solve these kind of problems in the TCP. Is this fine to everyone? So what I'm trying to say here is that if ACK is delayed, then this protocol itself won't work. So that is why don't worry about the delayed ACK. Actually, in TCP, we will see that if the ACK is delayed, and I mean, somehow we will make sure that even if the ACK is delayed, okay, even if the ACK is delayed, then also we cannot accept this ACK. This ACK, if this ACK is delayed, then this will automatically get expire, right? This will automatically get expire if the ACK is delayed. Okay, so if this ACK is delayed, then in TCP we will see that this delayed ACK will automatically get expire. Is this okay to everyone? So we will look at this delayed ACK later. Okay, so delayed ACK and delayed data, these things get automatically expire. I mean, this is no longer valid ACK. Okay, we will see how we will invalidate this ACK. Okay, basically this is a collection of sequence number and wraparound time or something. Okay, so I will tell you later in the TCP. So here, whenever we are dealing with these questions, don't worry about the delayed ACK. Now just worry about only two things. What are those two things? If data is lost or ACK is lost. Okay, don't worry about ACK delayed or data delayed. Okay, so delayed, don't worry. Is this okay? Just worry about lost thing. Now, if you are sending ACK, okay, so you are sending these 5 packets, 4 packets, 5, 6, 7, 8, maybe any 4 packets. Now tell me, is this possible at this moment in time? Can you receive the ACK from 3? Not possible, right? You have received the ACK from 3, then only you have selected the window. You have already received this, right? Yes, these are already acknowledged. Yes, Akash, that is correct. Because you have received, then only you have selected the window. You have received this, then only you have selected the window. So it is not possible to receive the ACK for 3 and 4. Similarly, it is not possible to receive the ACK for 9, 10 or any other future sequence number, right? Okay, don't worry about the delayed ACKs. Okay, but yeah, in general, you can't you won't be receiving the ACKs for 3 and 4 because you have already received it. You will be receiving the ACK for 5, 6, 7, 8 only. Is this fine? Okay. Okay. I mean, delayed ACK, it means that too much delayed. Okay. I mean, if it is, this can alter little bit, but what I'm saying that if it is too much delayed, that you are saying that, okay, I mean, it is coming from, from too much of past, then don't worry about it. Okay. Yeah, little bit reordering can happen in this particular. Let's suppose if it is sending 5, 6, 7, 8, if it is sending 5, 6, 7, 8, then little bit reordering may happen, which means I'm not saying that it will be receiving 5, 6, 7, 8 in order. Is this really possible that to receive for the sender the 5, 6, 7, 8 in order? It may be reorder a little bit, right? Which means that 6 it may receive first, then maybe 7, then maybe 5, then maybe 8, which is fine to us, right? Okay. Okay. So here in SR protocol, is this possible to receive the ACK which is outside the window? No, because the moment you shift the window, it means you're confirming that all the ACKs here has been received. Then only you're shifting the window. So is it possible to receive the ACK for 3 and 4? The answer is no. Okay. With go back N, is this possible for the sender to receive the ACK for packet that falls outside the window? Is this possible in go back N? What do you think? See, in go back N, what we use the cumulative acknowledgement, right? Which means, let's suppose I'm saying this is 5, 6, 7, 8. And whenever you are sending, let's suppose 5, 6, 7, 8, right? So it will be sending the ACK 4. I mean, depending on that, you are sending the ACK for 2 packets or maybe after 2 minutes or something like that. But it will be cumulative acknowledgement. Let's suppose it is saying that, okay, I'm sending the ACK for 6 and I'm sending ACK for 8. So can you tell me ACK for 6 means what will the ACK number? What is the ACK number? No, ACK for 6. ACK for 6 means I'm acknowledging that, okay, 6 has been arrived, which means ACK 7. Okay. Which means ACK 7. Okay. So here in ACK for 8 actually mean I mean to say ACK 9. Okay. Anyway, but I hope you understood that okay, we are sending. Now suppose there is some little bit reordering that is happening, and because of that you get this 8, and after that you receive this 6. Okay. Now if you are getting this 8, see, within the window there is a possibility of reordering. Okay. Which means that whenever you are sending it back to back, then there is a possibility of reordering. But outside the window, I mean, if it is too much delayed, okay, if it is too much delayed, just like this, then these kind of problems will be solved using some technique that we will see later in the TCP. But a reordering can definitely happen. Okay, reordering can definitely happen, which means that 2 and 3 may reorder a little bit. But if it is too much reordered, okay, then I mean, basically we will make sure in TCP that whenever it is too much delayed, I mean, little bit delayed is okay. Okay, we will see the reason why it is okay, and too much delayed is not okay. Okay, we will see the reasons in later in TCP. I don't know if I can explain it here or not, but if you like, I can give you the idea. So the idea there was we will be using is that see, we will be saying that, okay, we will be having the sequence number large enough. Okay, sequence number large enough, which means from 1 to maybe some big number, big sequence number. Okay, so whenever you are repeating this one, okay, this data packet 1, and then whenever you are again sending this one, between, I mean, just to from this one, you will be having 1, 2, 3, 4, 5, 6, 7, and directly you won't be getting 0. I mean, so after 7 there will be many other sequence number, and then you will be getting this, you will be restarting. So basically what I'm saying, that in TCP we will see that if there is any sequence number, let's suppose the sequence number is 5. Now the after this 5, to get this 5 again, okay, to get this 5 again, it won't be just after 1 minute or 2 minutes. I mean, it won't be too soon. It will be after 5, there will be 6, 7, 8, 9, 10, 11, and there will be too much sequence number. And if you want to repeat this 5 again, then it is automatically has been a long, okay, a long before you repeat this 5 again. That's what we will make sure in TCP. Okay, that I mean, we will be repeating the sequence number. Obviously we have to repeat the sequence number. We can't keep on incrementing the sequence numbers, but the moment you repeat it, it has already been very fast. Okay, and at that moment the timer of this particular ACK or the particular data number or the particular ACK number, this will automatically be expired. Okay, we will see this later in TCP, but maybe you might get little bit idea that there will be some timer. I mean, for which I will say that okay, this will be alive in the network for this much time, and that time for which it is alive. Okay, time for which this packet is alive, and the time for repeating the sequence number. Which time should be greater? Which time should be greater? If I'm repeating the sequence number, then this is greater time. Let's suppose I'm after 10 minutes, I'm repeating the sequence number. Okay. After 10 minutes, I'm repeating the sequence number, and this is alive only for 5 minutes. Any packet is alive, let's suppose only for 5 minutes. Then if I'm repeating the sequence number after 10 minutes, now the moment I get this one, now 10 minutes has already been passed, right? And then by this moment, I'm repeating the sequence number. By this moment, this is already expired. So even if I receive this later on, it doesn't matter to me, because it is already expired. Are you getting a little bit of idea what I'm trying to say? See, for every packet, I will say that there is a timer. Okay. I mean, it will be alive just for 5 minutes. In the network, I cannot accept this packet after 5 minutes. After 5 minutes, I will say that, okay, this packet is expired. This packet is containing some old information, which is not relevant in today's world. Something like that. Okay. So I will say that, okay, after 5 minutes, this packet will be completely discarded regardless what it contains, what it not contains. Okay. Which means that if this packet has been received to any host or any router or anything, it will immediately discard it. Something like that. Okay, because 5 minutes are over. It will just check whether its time is over. If its time is over, I will completely discard it. Now, let's suppose after 5 minutes, I'm saying it, I will discard. I mean, this packet is only live for 5 minutes. And if it is reaching here, and by this moment, from this one to this one, how much time has been passed? Can you tell me? If I'm repeating the sequence number, then I will repeat after how much time? After 10 minutes, right? After 10 minutes, I will repeat the sequence number. So if I'm saying that, okay, after 10 minutes, I will repeat the sequence number. And if I'm getting the ACK after 5, I mean, which is already expired after 5 minutes, does this really make sense? I mean, does this really be any harmful for me to get the sequence number later? No, right? Because I will anyway discard it. I will say that, okay, this is too old, right? This is too old. So that's how we will be solving this problem in the TCP. Okay, I will later on tell you. But I hope you got the little bit of idea that how we are solving the delayed ACK or delayed data problem in the TCP. That I will say that, okay, for every packet, there is a timer, and that will be live for this much time only, right? For example, this is live in the network just for 5 minutes. And if I'm repeating the sequence number after 10 minutes, after every 10 minutes, if I'm repeating the sequence number, then it doesn't matter. After 5 minutes, it will be completely discarded, completely invalidated. And even if I'm getting it later on, okay, after 5 minutes, if I get it, then it doesn't make any harm to me. And if before 5 minutes, if I'm getting it, if I'm getting it, then it is okay, because I'm not repeating the sequence number. So there is no ambiguity. If before 5 minutes I'm getting it, then my sequence number is already not clashing with, I mean, I'm not wrapping around the sequence number. So my sequence number could be 300 here, 300, 300, 301, 302. If I'm getting AC given, I will get to understand, okay, it is old one. Or will I get confused that it is new, it is old one or new one I just sent? See, if I'm at here 300, 301, 302, and if I get ACK one here, okay, before 5 minutes, will I get confused that, okay, it is new one, or I just recently sent? Have I recently sent this packet number? I mean, from the packet one or something like that? No, right? I have recently sent 300, 301, 302, right? So even if I'm within the 5 minutes, if I'm getting, since there is no ambiguity because I'm not wrapping around the sequence number, then it is fine, right? I mean, I will completely ignore it. But if I'm getting it after the wraparound, then I'm making sure that it is already expired. Okay, this trick we will be applying in the TCP. Have you understood that what I'm trying to say? Okay, cool. So anyway, I mean, this is what I'm trying to say, that if it is too much delayed, I mean, if it is even after the wrapping around of the sequence number, I will anyway discard it, but little bit reordering is anyway happening, right? Will anyway happen. So coming back to this question, let's just see this question, what this question is saying. In Go backend, it is possible for the sender to receive an ACK for a packet that falls outside the current window. So what does this mean? Let's suppose you're sending some 4 packets, 5 packets or anything, 5, 6, 7, 8. Okay. The sequence number could be anything, but it should be in the sequence. I mean, it cannot be some random. It cannot be 3, 9, 100. It cannot be random. It should be in the sequence. You can start with anything. 100, 100, 01, 100, 02. 100, 03. This is also fine. I mean, 1 or 3. Okay. So this is also a very much fine sequence number. So you can have any 4 sequence number, but that should be in the sequence. Now, suppose you're sending 5, 6, 7, 8. Is this possible that you are getting ACK for 6, which is ACK 7, and ACK for 8, which is ACK 9? But let me not call it 7 and 9. I mean, I'm just saying ACK for 6 and ACK for 8. Is this possible to have the little bit reordering? Definitely possible, right? Definitely possible to have this reordering. Now you tell me, if you reorder this, then at this particular moment, now you will be getting this ACK for 8, which means you will say that, okay, since you have got ACK for 8, doesn't this mean that everything has been reached till 8? So the moment you receive the ACK for 8, you will immediately shift your window. I mean, your window is 5, 6, 7, 8, but you immediately shift your window outside the 8. So this 8 will be outside the window, right? So your new window will be 9, 10, 11, 12, isn't it? This is your new window. Now, if you're getting, after shifting this new window, if you're getting this ACK for 6, isn't it falling outside the window? Tell me, isn't it falling outside the window? Yes, right? Because this ACK for 6, ACK for 6 is basically, I mean, ACK for this particular packet, then that definitely it is falling outside the window. So in go back in, is this possible? Then answer is yes, right? It is definitely possible in go back in. But is this possible in a selective repeat? The answer is no. The reason being is that I must have shifted only when, see, here I'm shifting even without getting ACK for 6, right? Am I shifting based on ACK for 6 or am I shifting based on ACK for 8? ACK for 8, right? Even without worrying about ACK for 6, I am shifting. But in selective repeat, can I shift even without worrying about ACK for 6? No, right? So I must be getting ACK for 6 and then only I'm shifting, right? So that's how I'm shifting in the selective repeat. So that is why if I'm at 9, 10, 11, 12, if this is my new window, 9, 10, 11, 12, it means that I must have received all of these ACKs, right? All of these ACKs already. I must have received all of these ACKs already. Okay. If I'm shifting my window, it means that I must have received all of these ACKs. And in go back in, if I'm shifting my window, in go back in, then it doesn't mean that I have received all of these ACK. Maybe I've received just one of them, right? Which is the higher one. And then because of that, maybe I have shifted. And once I shift it, it is possible. It is definitely possible that I'm getting this particular, I mean, next ACK. And there is no ambiguity in this. I mean, I will be just ignoring it, right? I will just say, okay, let's just ignore this. Anyway, so let's just solve more problems and you will get to understand these protocols more. Okay. Let's just see this question. So what this question is saying, after transmitting several times, the transmitter received a negative acknowledgement I frame. Okay. NAK I frame. I'm negative acknowledgement for some frame. Do you remember what does this negative acknowledgement mean? Can anyone tell me? Negative acknowledgement in any protocol, what does this mean? It means that I have not received. I have not received. Can anyone complete this frame? Can you tell me that? Okay. Yeah, frame number I. The negative acknowledgement means I have not received this frame number I, right? That's all. So they're saying after transmitting several times, the transmitter receives, I mean, the transmitter means sender, okay? So transmitter means sender. So the sender receives negative acknowledgement. Describe how that sender reacts in the following protocol. So in go back and what it will do? In selective reject, it is also called selective reject or selective repeat. So what it will do? So in go back and it will send all the packets from I to the whole window, right? So, I mean, what is the retransmission it will be doing in go back in? How many packets it will be sending? Yeah. So in go back in, it will be sending I to I plus n minus 1. I mean, if you count the number of packets in this window, it will be n packets, right? In selective reject or selective repeat, it will be sending just ith packet. Okay. Just ith packet. right? Okay. Describe what happens if negative acknowledgement is lost during the transmission in the go backend protocol. I mean, if the negative acknowledgement is lost, then what do you think? What will happen? Timer will take care, right? Yeah, timer will take care. I only subsequent. Okay, so that is the answer. I mean, this is the answer that we have just seen. Is this question okay to everyone? Now let's just solve next questions. Okay, I mean, let's just first see this concept, which is very much necessary. It is called efficiency and throughput. Okay, so is there any question till now? Okay, so now let's just see the concept of efficiency and throughput in sliding window protocol. And what are those sliding window protocol? These are the two types. What are these? Go backend and selective repeat. Right? Do you remember the efficiency or the throughput in the stop and wait? Do you remember? Can anyone tell me that what is the efficiency in stop and wait? Yeah. So efficiency was TT upon RTT. Yes. Right. And RTT is also I mean, it is in most of the places, it is TT plus 2TP. Right. Okay. TT plus 2TP. So basically this was the efficiency in the stop and wait. Or in other words, like if you write it like TT upon TT plus 2TP, then you can say that this much time you are utilizing out of this much time. That was the efficiency, right? Or in other words, you can say this is 1 upon 1 plus 2a, which means that, I mean, in terms of the packet, you can say that these many packets you are sending and this much you could have sent, right? So efficiency you can write in many ways. We have seen that in terms of time, you can say in stop and wait, I'm telling you, right? In terms of time, you can say you are utilizing this much time out of how much time? TT plus 2TP, right? In terms of time, you can say something like this. In terms of packet, you can say that, okay, you are sending one packet, what you could have sent 1 plus 2a packets in RTT time, right? In terms of packet, you can say something like this. And in terms of bytes also, if you want, you can say something like this, that you are sending how many bytes? You are sending L bytes, but you could have sent how many bytes? In RTT time, RTT into bandwidth, right? Yeah, RTT into bandwidth. I mean, anytime you can send these many. I mean, if someone asks you that in TT time, how much you can transmit, then TT into bandwidth in any time. Okay, you need to multiply by the bandwidth. That is also called. There is some specific name for this. Can anyone remember? I mean, I have not even told you too much about it, but I think I just named it in one of the lecture. So what this is called? Yeah, this is basically called bandwidth delay product. Okay. Bandwidth delay, okay, product. So what does this bandwidth delay product says? It says that how much number of bytes you can send in RTT time. That's called bandwidth delay product. Okay. Okay. I mean, in any time, basically, if this is, let's suppose, TP time, and how much bytes you can send, TP into bandwidth, right? TP into bandwidth. Or in any time, if someone asks you that how much bytes you can send, then that into multiply with bandwidth, right? So efficiency can be written in many ways. Do you remember that efficiency can also be written in what is the, I mean, maximum capacity of the channel, which means maximum transmission rate, which is bandwidth, and what you are actually sending. Can you tell me what you are actually sending? What we call it? We call it throughput, right? Yeah, we call it throughput. What we are actually sending is called throughput, and what we could have sent, I mean, with what rate we could have sent, it's called bandwidth. So efficiency can be written in many ways. Okay, maybe like this, or like this. And also this particular formula, which is efficiency and throughput bandwidth relationship, can also be obtained in one other way. How? I mean, this is one way to look at this formula, and there is one other way to look at this formula, which is efficiency, throughput, and bandwidth. I mean, this particular relationship. So by the way, like all of this are equal. I mean, this term, this term, this term, this term. I mean, all of these 4 terms are equal, right? It is just a different way of writing. Okay. Now, I was saying that we can write this throughput as how much bytes we are sending in RTT time, right? RTT, and how much bytes? The length of the frame, L upon RTT. Is this okay to everyone? This is how we can write the throughput. How much bytes we are sending in RTT time, right? I mean, this is the basic definition of the throughput. Okay. Now, if you relate, let's suppose you don't know this. I mean, let's suppose you don't know this particular formula. I mean, logically, let's suppose you don't know this, right? I mean, you can just discard this for now. Okay. Suppose logically you don't know this, then can you establish the relationship between throughput, efficiency, and bandwidth? So can you see that this formula of throughput and this formula of efficiency are nothing but related by bandwidth, right? Related by bandwidth. So basically you can definitely write that efficiency or the throughput is nothing but, see, this is throughput, right? So this is efficiency. So you can say throughput is nothing but bandwidth into efficiency, right? Bandwidth into efficiency. So throughput is nothing but efficiency into bandwidth. Okay. So that's how we can also drive this formula, right? I mean, this relationship between efficiency, throughput, and bandwidth, right? That's how we can drive it. But logically also, I think this makes sense to us, that why we are writing something like this. Is this okay to everyone, that how all of this makes sense in stop and wait? I mean, this is just a quick revision that we have seen in stop and wait. In quite a detail we have seen, right? Okay. Now let's just see for the sliding window protocols. Okay. For the sliding window protocols. So how many packets you are sending in RTT time here? Let's suppose the window of the sender window size is, I'm writing in W as equal to N. The sender window size is N. So can you tell me in RTT time, how many packets you are sending? This is 1, 2, 3, right? So let's suppose that I'm measuring the RTT from here and you are getting here. Let's suppose these are the some packets. So can you tell me how many packets these are? These are N packets, right? N packets. So you are sending basically N packets in RTT time. Okay. I mean, there are many ways to look at it. You can say that, okay, you are utilizing how much time? How much time you're utilizing? N into TT. Right? N into TT time you are utilizing out of RTT. This is one way to look at the efficiency here. I mean, it is just N into N into the stop and wait, basically. Okay. So which means N packets you are sending out of how much you could have sent here also. So in RTT time, you can send how many packets? In RTT time, you can send 1 plus 2a packets. What is the RTT time? RTT time is the time that you get your first ACK, right? You get your first ACK. I mean, if you want to get this ACK for this particular packet, then you will be getting after RTT time. Okay, this is the time that we call RTT time. So basically, you will be sending N packets, but you could have sent 1 plus 2a packets, or you are utilizing basically N into TT time, but you could have utilized RTT time itself, right? So this is the efficiency. That's all. And this efficiency is basically same in this go back and in the selective repeat, which means the efficiency is same here because we are sending the same number of packets. Okay. So the efficiency for go back and selective. Here N is sender window size or receiver window size? Yeah, sender window size. Okay. Now you must be wondering, if both are having this, both are same efficient, then what is the use of the selective repeat? I mean, why we are basically having multiple packets in the selective repeat at the receiver? I mean, if the go back and selective repeat both are the same, having the efficiency, okay, then what is the use of that? Okay, so what is the difference? Yeah, if lost packet and need to send and go back and then only, yeah. So the difference will be, difference, you people are right. The difference is not, if you are not having any packet lost, right? If you're not having any packet loss, then both are same basically. But if you are having the packet loss, then this is not the efficiency actually. Okay, and the calculating the efficiency will be too much complex basically. Okay, if you are having the packet loss, then calculating the efficiency in go back and or selective repeat is too much complex. I mean, that's where we need to do the probabilistic analysis, which means that, okay, probability of losing some packet is p. Then in go back end, what is the expected time to send n packets, and based on that, see, tt time we are utilizing, and what is the expected time, we need to write it here. And I mean, ntt plus maybe, I mean, extra time that you are utilizing, right? I mean, so basically you need to yeah, entity will be there, I think, on the numerator, because that's the time that is the effective time. But out of that, I mean, how much total time you will be taking won't be just RTT or something, right? It will be basically much more than that, because the packet can be lost or something. So basically that analysis, which is very, very complicated, and it is not required for gate. Okay, so this is the efficiency where there is no packet loss. Is this clear to everyone? If there is a packet loss, then what will happen? See, this is the efficiency when there is no packet loss. Okay, if there is a packet loss, then the calculating efficiency is not a a piece of cake basically. Okay, it will be too complicated, and it is not required for gate. It is completely not required for gate. Okay, I mean, not even the analysis, not even the formula. The formulas are there, but these are the two complicated formulas, right? If there is a packet loss, and they have not asked in gate because it is beyond the syllabus. Even it is not given in the textbooks. Okay, I mean, these probabilistic analysis, if the packet is lost, then these analysis are not given in any textbook, any textbook, which means the textbook which I'm referring to. So I'm referring to these textbooks for our this computer networks purpose. So this is not given, as far as I have seen all the textbook, if I remember correctly, then it is not given. The probabilistic analysis are not given there, right? So, and also it is not required for gate. If there is no packet loss, then this is the efficiency in case of go back and selective repeat. Now, obviously, now you have the little better command. Now, it is possible that they may ask the tricky question. Tricky in the sense that they will be just altering which thing, the RTT thing. I mean, they will be having the maybe the processing time. They will be having the queuing delay or something, right? In that case, you need to write NTT upon RTT. Okay, if RTT definition is basically not TT plus 2TP, then you can take care, right? Is this okay that you can take care? I mean, we will be seeing the questions, don't worry. But before seeing the questions, are you getting the confidence that, okay, you can say that, okay, this much time you're utilizing, out of how much time, right? If they give you some other things about the RTT, I mean, there's a processing delay or something, then you can actually, it is n into stop and wait efficiency. Okay, you just find out the stop and wait efficiency, you just multiply by the n, and your answer will be always correct. Okay, so let's just see the questions. Maybe after that you will be getting more confidence. Okay, so this formula is without the packet loss, and also this 1 plus 2a I'm writing, assuming that RTT is which one? Can you tell me? Assuming that RTT is TT plus 2TP, right? If RTT is this, then I'm writing this formula. Okay, if they give you some other definition of RTT, then, I mean, some other numbers in the RTT, then maybe the formula will be a little bit different. I mean, we don't need to obviously consider all the formula, but I hope you understood that ultimately it is, you can say, it is NTT upon RTT, right? This is the final formula, you can say. In terms of time, this is the final formula. Okay. This is the final formula. But actually, in most of the time in the questions, they will directly give you TTTP. So it is convenient to use this formula. I mean, n upon 1 plus 2a. Okay. Let's just see the questions and you will be more familiar. But yeah, this is the final formula in the sense that if they alter the definition of RTT, this is fine to you. Okay. Even if they alter the definition of RTT. Now let's see this question, what they're saying, and then you will be getting little more confidence about the efficiency and throughputs. Okay. So suppose that, okay, maybe this question is little long. Maybe I can do little, I mean, I will come back to that question. That question was also easy, but let me first solve this question. So what they're saying, suppose that it takes 1 millisecond to send a packet with 10 millisecond one-way propagation delay. So transmission time is given to you 1 millisecond. Propagation time is given to you 10 millisecond, right? Between the sliding window protocol and the size of the window is given 4, then channel link utilization is nothing but efficiency. Then they're asking the efficiency. Can you tell me the efficiency here? It is n upon, so this is 4 upon 1 plus 2 into TP, 10 upon 1, right? So what is the answer? This is 21. This is 4 upon 21, right? Okay, which is 0.19. So 0.19 is your answer. Easy question, isn't it? Let me know if you have understood this. You just need to apply n upon 1 plus 2a. Okay. Now let's just solve this question. This question is also easy one. So let's just solve this question. What they're saying, suppose we have a network connecting two hosts with RTT of 100 milliseconds, which means RTT is given to you as 100 milliseconds. And a bottleneck link rate is 30 megabits per second. So if this is the bottleneck link rate, which means what is given here, it is the bottleneck bandwidth, right? So which means, I mean, there could be multiple connecting nodes and the bottleneck bandwidth is 30 megabits per second. Now they're saying, assume that packet size is 1500 bytes. So length is also given to you, it's 1500 bytes. Okay. What is the maximum throughput that you can achieve? Maximum throughput is basically nothing but the bottleneck bandwidth, right? So, I mean, irrespective of the protocol, don't worry about the protocol, that they have not asked you about any protocol. Okay, whatever you do, whatever you want to do, what is the maximum throughput that you can achieve? It is a bottleneck bandwidth, right? Or the bandwidth. I mean, if it is just one link, then it is a bandwidth. So it will be, can you tell me what is the answer here? It will be 30 megabits per second. So it is 30 megabits per second. Right now they're asking about the stop and wait. So in standard one packet stop and wait, what is the percentage that maximum throughput will be used? So see, let's just find out the transmission time here. So what is the transmission time? This is 1500 bytes, right? And in bits it will be like this. Then this much bits divided by the bandwidth that you can use, which is 30 megabits per second, right? 30, if it is in mega, multiply by 10 to the power 6. So ultimately this is in second. Now if you want, you can convert that to in the millisecond by multiply by 10 to the power 3, right? So it will come out to be 4 milliseconds. So which means the transmission time is 4 milliseconds. RTT is also given to you. Now what they're asking is that, okay, what is the throughput that you can use? So yeah, RTT is already given. So I think you don't need to find out the transmission time here also, right? But anyway, so yeah, transmission time explicitly is not required. So what you can say, that if they're asking you throughput, then what you can say, you are sending 1500 bytes in 100 milliseconds basically, or you can say in 100 milliseconds you are sending 1500 bytes, right? Now can you tell me in 1000 milliseconds or maybe in 1 second how much you are sending? Which means in 1000 milliseconds or in 1 second how much you are sending? 15 into 10 to the power 3 bytes. Is this okay to everyone? Let me know. So these many bytes you are sending, right? Okay, maybe I can remove this calculation because it was not even required. So these many bytes you are sending, right? So which means 15 into 10 to the power 3. This much bytes per second. This much bytes per second. But if they ask you, let's suppose the throughput in megabits per second. Okay. So to convert that into bits, you need to multiply by 8, that will be bits per second. But if they ask you megabits per second, then you need to divide by 10 to the power 6, right? So this is megabits per second. Now, if you see, that answer will be this is 120. Is there something wrong that we have done? In 100 milliseconds, you are sending 1500 bytes, right? Yeah. So this will be 0.12 megabits per second, right? In megabits, you are getting this much answer. Let's just see what is given here. Yeah, 0.12 megabits per second, right? Okay. So 0.12 megabits per second that you are getting. But what they're asking is that what percentage of the maximum throughput? Okay, they're not asking actually the maximum throughput that you can achieve. They're asking the percentage of the maximum throughput, which means what they're asking. This is other way of saying what? Efficiency. This is other way of saying efficiency. Okay. So they're asking the efficiency actually. So what is the efficiency? Efficiency is nothing but whatever is the throughput that you are getting upon what is the maximum throughput that you can get, right? I mean, there are many ways to calculate the efficiency. So you can calculate in this way, which is the divided by the maximum 30. Okay. So it will be 0.4. Sorry, 0.04, I think, right? 0.4 or 0.04. Yeah, it will be 0.4. Okay. So 0.4 is the maximum throughput that you are getting. Okay. I mean, percentage of percent. I mean, in terms of percentage, I'm writing. Okay. In terms of percentage, I'm writing. So, which means, see, you have got 0.12 is the throughput here, right? And bandwidth is given to you is 30 megabits per second. This is also in the megabits per second. So, what is the efficiency? Okay, 0.12. This is in reality, you are doing this. You could have done this in percentage. You can multiply with this, right? Okay, sorry, this will be 0.04. Yeah, this is ultimately 0.4 percentage. In percentage, it will be 0.4 percentage, right? Is this fine to everyone? Okay, so this is the percentage that you're using. Now, let's just see this question number C. Now, suppose if instead of using this stop and wait protocol, you use the sliding window protocol, then what is the efficiency then? Whatever you got the efficiency, you just need to multiply by n. So can you tell me the efficiency in terms of n? It is n into 0.4 percentage, right? That's all. Okay, 0.4 into n. So whatever you got earlier, you just need to multiply by n. That's all. That is how we can solve this particular question. Okay. Now, let's just move to the next question that we have. And even before moving to the next question, let's just see the relationship between the window size and the available sequence number. This is the final concept that we need to know to solve any of the question related to sliding window protocol. So let's just see this concept and then we will be solving many PYQs, okay, back to back. Cool. So what does this even mean? Let me just first tell you. So here, let's suppose that you are having many packets to send. Can you write the packet number as 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11? Can you write packet number like this? Let's suppose you have 12 packets to send at the sender. You can definitely write the packet numbers like this, right? I mean, it depends that, okay, how many bits. If you have, let's suppose 3 bits available with you, then probably you will be writing, you will be basically making 12, 13, 14, 15, right? If you have 4 bits available with you, right? You can number like this. If you want, I mean, it is up to you. I mean, there is no such restriction. If there's a restriction, we will see. But if you have 16 packets, you can number like this. Can you number like this if you have 16 packets? If you have 16 packets, can you number them like this? What do you think? Most probably yes. Okay, most probably yes. I mean, we will see if there's any restriction, but most probably yes, right? Might be able to write like this. We might be able to write like this. Can you write if you have 16 packet? Can you number them like this? What do you think? I mean, till 7, then you're repeating. If you have 16 packets, can you write like this? Most probably yes, right? It is just a numbering. Is this clear to everyone that we are just numbering the packets? Okay. This 0 is containing the different data than this 0. I hope that is fine to everyone, right? I mean, this 0 is whatever the data this packet 0 is containing is not the same data this is 0 containing, right? This is just a numbering at the data link layer we are doing. It doesn't mean that these two are containing the same data. I mean, the application layer or the upper layers might not be sending the same data. And anyway, why they will be sending the same data until and unless that is required, right? So these two, the sequence numbers are same, doesn't mean that these are containing the same data. And that's what you already know, right? Okay. Now, let's suppose you have any protocol. Maybe it is go back n, or you have selective repeat. Okay. Any protocol that you have, there is some window of that protocol, right? Now, let's suppose you have, okay, you want to send some packets and the packet numbers are like this: 0, 1, 2, 3, 0, 1, 2, 3. 0, 1, 2, 3. Okay. Suppose these are the packet numbers that you have. This is at the sender side. Okay. This is at the sender side. Now, what I mean, what I want you to ask, what I want to ask basically here is that can you just send, I mean, can one window, okay, can just one window contain all of these packets? Can just one window contain all of these packets? What do you think? Can you send all of this packet at once? Will there be any problem here if only one window contain? So the answer is yes, there will be the problem basically, right? You cannot send all of this at once. What do you think? What could be the problem? Let's suppose that you have how many? This 4, 8, okay, 12 packets, right? These are the 12 packets. Then if you send them once, which means if you're sending them 0, 1, 2, 3, 0, 1, 2, 3. Let's suppose RTT is big enough. Don't worry about the RTT. That okay, if RTT is small, then how I will be able to send. Don't worry about the RTT. There is no limitation on the RTT in the sense that you have good RTT here, right? Which means that, I mean, the RTT, see, you cannot send, you cannot keep on sending after the RTT. So basically you will be, I mean, let's suppose RTT is here and you are sending something like this, right? 0, 1, 2, 3. Okay. Can you send all of these packets just once, even if RTT is too long? The answer is no. Why that is the case? Why you can't send? Don't worry about the RTT and all, but tell me why you can't send all of this at once. The reason being is that if you are having two packets with the same sequence number in the flight means in air. If these are the two packets with the same sequence number in air, then there will be the problem. Okay. If there are two packets with the same sequence number in the air, then there will be the problem. What is the problem that you may get? See, just try to understand what I'm trying to say. That if you send this all of the packet at once, then you're intentionally creating the problem. See, suppose on contrary, if you're only sending 0, 1, 2, 3, and once you receive the acknowledgement for 0, 1, 2, 3, then you are sending the next 0, 1, 2, 3, then there is no problem. Okay. Once you acknowledge them, then you are sending the next 0, 1, 2, 3. There is no problem. Okay. Why that is the case? Because there is no confusion here. See, at the receiver side, just assume. Okay. I will come to this case, but for now, just assume in this case. At the receiver side, just assume. Okay. Just assume the case that this 0 and this 0 is little bit reordered, right? Little bit reordered. Then receiver will think that this is the first 0. Receiver will think this is the next 0. Won't it be the too much problem? If you're having the same sequence number in the flight, then you're intentionally creating the problem, right? These are not duplicate packets. These are different packets. Basically, receiver here will think it is waiting for, let's suppose, packet number 0, packet number 1, packet number 2, packet number 3, packet number 0, packet number 1, packet number 2, packet number 3, and so on. Receiver will think that this is the first 0, receiver will think this is the next 0, and then packet want to be delivered in order. Okay, I mean, receiver, this is the, let's suppose, data link layer, then it want to be delivered to the upper layer. Receiver has to pass those to the upper layer. Receiver by mistake say that, okay, this is the packet number 0, which was the packet number actually not 0. I mean, this is the not the first 0. Receiver think that this is the first 0. So for example, you are sending some data, maybe some image you are sending. Okay, so for example, it may so happen if this is your face, okay, and then you're let's suppose this is getting in the chunks, this image is getting in the chunks, then maybe receiver will think that, okay, this I is a I mean, the receiver will think that, okay, this is the I. Okay, I mean, let's suppose this is also packet number 0, this is also packet number 0. So you are sending, you want to send this, okay, you want to send this, and receiver will be delivering it like this. Here it will say that, okay, this node it will putting here, and this node it will be putting here, the I it will be putting here. I mean, it will reorder, right? You will think that, okay, I have sent the correct human image, this is how the node is here instead of I. You're getting my point? So the reordering is obviously, I mean, receiver won't be able even able to get that if it is reordering. Okay, I hope you understood what I mean to say. So if you're intentionally creating a problem, it is not making any sense. So obviously you want to be sending in a flight, you want to be having multiple packets with the same sequence number. Okay, which means that you can say that if you want to send these packets, then you are most welcome to send, but you should not send 0 and 0 in once. Okay, once you receive the acknowledgement for this 0, then you send this 0, no problem. Okay, then you send this 0, no problem. So that is why you send 0, 1, 2, 3. Okay, can you send this much? If not this much, can you send till this point? Can you send till this point at once? What do you think? Can you send till this point? No, right? Even if the two packets are having the same sequence number, they should not be in the flight at once. Okay, they should not be in the air at once. So you cannot send these two also. You can send 0, 1, 2, 3, definitely. Distinct, you can definitely send. Can you send only 0, 1, 2? Can you send only 3 at once? Even though you have, you can send 0, 1, 2, 3, but let's suppose you only are sending 0, 1, 2. Is this possible? Yeah, this is possible. If this is underutilization or something, this is definitely possible. Okay, this is definitely possible. Now this is 0, 1, 2. You can definitely send it, but let's just send 0, 1, 2, 3. Okay, I hope that is fine. Now, I mean, suppose, okay, suppose I'm just sending 0, 1. Okay, now receiver will be waiting for which packets? Receiver will also be waiting for 0, 1, right? Will also be waiting for, this is the receiver. It will also be waiting for 0, 1. When 0 is arrived, I mean, if it is go back and it will be only waiting for one of them for 0 only, but let's suppose it is selective repeat, it is waiting for 0, 1. When 0 is arrived, it will say, I arrived, this has been reached, right? So basically it will be sending, once it get it, it will be sending the data, right? That, sorry, the acknowledgement. It will be sending acknowledgement for 0. It will be sending acknowledgement for 1. Is this okay to everyone? These two acknowledgements it will be sending. Okay. Now the next packet, can you tell me which one? What is the next packet that you should be sending here? The 0, 1 has been reached. So the window will slide. This is the current window, but the window will slide. Then the 2, 3, right? The 2, 3 it will be sending. So after the slide of the window, it will be sending 2, 3, right? Then it will be acknowledging 2, 3, and so on and so forth, right? This is the normal story that we can do. Okay. Now let's just consider one of the extreme case here, where let's suppose all the acknowledgement here by the receiver get lost, which means suppose just consider the case that all of these acknowledgements get lost, all of them. What will happen at the sender side? And what will happen at the receiver side? This is the interesting story actually, and this will establish the relationship that I'm talking about. So the sender will be having the timeout. isn't it? What receiver is waiting? This is also interesting. Receiver is waiting for 0, 1 or not? What receiver is waiting here? Receiver is not waiting for 0, 1, right? Since as per the receiver, 0, 1 has been reached. So receiver is waiting for 2 and 3, isn't it? Receiver is waiting for 2 and 3, but acknowledgement is lost. So it will be sending 0, 1 and again. Now you tell me, what will receiver do for this 0, 1? What this receiver will do? It will definitely discard it and so on, right? It will say that, okay, I mean, after discarding it, it might say that I'm expecting, maybe it can say the NAK for 2 or something like that, that I'm expecting, that it can say that I'm expecting this 2 or 3 or something like that, right? Okay. So it will discard that. Now, I hope this problem is okay to everyone, that if all AC keys are lost, I'm just trying to explain you what going to happen if all AC keys are lost. If all AC keys are lost, it will definitely retransmit the packets, but receiver will discard it, right? Okay. And it will work very fine, right? Receiver will discard it. It will not be having a duplicate data or something. Now, let's just consider a case where all AC keys are lost. I mean, we are in the case where all AC keys are lost, but instead of having in the window, the 0, 1, interestingly, you are having 0, 1, 2, 3, which means you are sending 0, 1, 2, 3. Okay. So at the receiver, you are waiting for what? Tell me. You are waiting for 0, 1, 2, 3. Now, once you receive all of these 0, 1, 2, 3, you will be sending the acknowledgement for 0, 1, 2, 3. Okay. You will be sending the acknowledgement for 0, 1, 2, 3. That's not an issue. You will say, okay, I have received this, right? Now, interestingly, suppose all AC keys are lost. What will happen at the sender side and what will happen at the receiver side? Sender will be sending 0, 1, 2, 3 again. Receiver will be saying that I'm waiting for what? As per the receiver, you are waiting for what? Next 0, 1, 2, 3, right? No. The packet sequence number is 0, 1, 2, 3, 0, 1, 2, 3, 0, 1, 2, 3. There is no 4, 5, 6, 7. Okay. That is agreed upon the sender and receiver. Okay. So the packet numbers are only 0, 1, 2, 3. So receiver is waiting for 0, 1, 2, 3 again. So it is waiting for receiver. You got 0, 1, 2, 3. What will happen? What will happen? Tell me. Receiver will be accepting these packets. Receiver will be accepting this 0, 1, 2, 3, isn't it? See, receiver is waiting for next 0, 1, 2, 3, and you got the 0, 1, 2, 3. So receiver will be basically accepting this 0, 1, 2, 3. But is this the correct accept or this is the problem? Tell me. This is a problem, right? This is definitely the problem. Receiver will be saying that, okay, I mean, something like this. I mean, it will say that instead of, let's suppose in previously it have received just, let's suppose head, okay, just head. This is the face, and in this face, like previously this 0, 1, 2, 3 is representing the head, okay. And now you're again saying that, okay, I don't have eyes, I have 2 head, okay. Instead of having 1 head and 2 eye, I have 2 heads. Is this the correct thing? No, right? I mean, you are saying that, okay, I don't have 2 eyes. Instead of that, I have 1 extra head. Obviously, this is not the correct thing, right? Or the 4 head or anything, right? Okay. So basically, this 0, 1, 2, 3 should have been rejected, but it will got accepted, right? See here, if you are sending just 0, 1, will this problem occur? Will this problem be occurring? Tell me. Here, is this wrong? Is this wrong acceptance? See, you are waiting for what? You are waiting for 2, 3, but the retransmission is happening for 0, 1. Right? I mean, see, whatever you are next waiting for and whatever is the retransmission is not colliding, right? You are sending 0, 1, which is the retransmission, and you are waiting for something else. But here there is a common thing. I mean, you are retransmitting 0, 1, 2, 3. And the next thing I'm waiting for is also 0, 1, 2, 3. So there's a common thing. That's why there's a problem. Let me just explain you one more time. I mean, with a different example. So suppose suppose here all ACKs are lost. Okay, just assume that all ACKs are lost. Now suppose you are sending 0 1 0 1 2. Okay, let's suppose you are sending 0 1 2. Okay, it will be ACK 0 1 ACK. I mean, it will be sending the ACKs, right? Now suppose all ACKs are lost. Okay, suppose, I mean, I'm considering a case where all ACKs are lost. Now after the timeout, you will be sending what? 0 1 2. You are waiting for what? Receiver is waiting. I mean, receiver have just got 0 1 2. You tell me, receiver is waiting for what? Can anyone tell me? The next thing, receiver is waiting for 301, right? So receiver is waiting for 3, 0 and 1. It is waiting for 3, it is waiting for 0, it is waiting for 1. You have sent 0 1 2. The moment 0 arrives, what receiver will do? Will accept or reject it? Tell me. The moment 1 arrive, what receiver will do? Will accept or reject it? Will accept it, right? 0 and 1 will get accepted. This 2 will get rejected, that I agree, but 0 and 1 will get accepted, right? Is this the correct accept or the wrong accept? So this is wrong accept, right? Now what is happening? Whatever you are retransmitting, if that thing, the retransmission thing, is coinciding with the waiting of this receiver, then there is a problem. See, if you are retransmitting 0 and 1 and receiver is waiting for completely different set of packets, then there is no problem. Are you getting my point? If you are retransmitting 0 1 2 3, receiver is also waiting for same 0 1 2 3, big problem. You're retransmitting 0 1 2, receiver is waiting for some part of it, then also, I mean, even if 1 is coinciding, then it is a problem, right? Even if 1 is common, even if 0 is common, or just 1 is common, then this is a big problem. Yeah, getting my point? Okay. Now let's just do one thing. Let's just try to solve this question. Okay, let's just try to solve this question. Now what they're saying, I mean, I will come to the solution, that what is the solution here, but let's just first understand the problem itself. Okay, so what is the problem? How we should be managing this problem, in the sense that what number of packets we can send. See, we cannot send this whole chunk at once, that is for sure. I mean, we cannot send all of this at once, right? This is understood to everyone, because little bit of reordering will create a huge problem to you. So you cannot have 2 packets in flight, okay, with the same sequence number. We cannot have 2 packets in flight with same sequence number. Is this okay to everyone? This is fine. I mean, this was little straightforward, right? But it seems like that even if that we are not sending duplicate or the same duplicate sequence number packets, we are not sending the same sequence number at once, still there is a problem, right? Are you getting my point? See, if you send 0 1 2 3 0 1 2 3, I mean, if you even send this, even if you send this, there is a problem. That is understood. I mean, if in flight at once, if you have 0 0, there is a problem. But it seems like that even if you are not having the common sequence number in flight, then also it is a problem. Is this problem understood to everyone? 0 1 2 3, it seems that you can't send, right? Similarly 0 1 2, it also seems that you can't send, because if all ACKs are lost, then receiver is waiting for 3 1 0, which is coinciding. I mean, some part of it is coinciding with whatever you're retransmitting, then also it is a problem, right? But can you send just 0 1? Can you send just 0 1? The answer is a big yes. Okay, you can definitely send 0 1, in the sense that if you send 0 1, receiver will be waiting for something which is not coinciding with your retransmission, then you can definitely send. Getting my point? Okay. So let's just solve this particular question, then we will come back to the solution. Let's just first try to understand the question. I mean, see, the problem here is that you can't send multiple packets with the same sequence number in flight, right? This is one thing. See, we cannot send multiple packets. Okay. Same sequence number packets in flight. Is this okay to everyone? Let me know. Okay. But it seems like are these two statements okay to everyone? But it also seems that we cannot even send all distinct, okay, all distinct sequence number at once. Are these two statements okay? I mean, this is the problem. This is the second number is a problem. Let's just see that what is the solution here. Okay, and what is the limit? Okay, if we cannot send, see, here I'm saying that you can't send 0, 1, 2, 3, right? Here I'm saying you can't send 0, 1, 2, 3. And then I'm saying you can't send 0, 1, 2. But then I told you that, see, you can't send 0, 1, 2, 3. You can't send 0, 1, 2, 3. Then I'm saying that you cannot send, just a second. See, I'm saying you can't send 0, 1, 2, 3. I'm saying you can't send 0, 1, 2 also. But all of the sudden I'm saying that, see, you can't send 0, 1, 2, 3. You can't send 0, 1, 2, but you can send 0, 1. So it seems like we can send, but the 0, 1, 2, 3 entirely getting the problem. Even this 0, 1, 2 is also creating the problem. But if we are sending little, which is 0, 1, then it seems that there is no problem, right? Are you understanding? See, the 0, 1, 2, 3 is creating the problem. 0, 1, 2 is also creating the problem because whenever you are retransmitting, just try to understand, whenever you want to retransmit, because of all ACKs are lost, in that case, whatever receiver is expecting is actually coinciding with your current retransmission. So that's why it is a problem. But here in case of 0, 1, it is not the problem. Right? In case of 0, 1, that what receiver is expecting? 2 and 3. What you are retransmitting? 0 and 1. Are these coinciding? Are these coinciding? No, right? No. So that is why we can definitely send. Okay. So let's just do one thing. Let's just, okay. Let's just see. I mean, I will solve the question, but maybe it is a correct time to let you know that what could be the maximum packets you can send for any given sequence numbers. Okay. So see, it seems that you can't send 0, 1, 2, 3. It also seems that you can't send 0, 1, 2. But it seems that you can send 0, 1. So what is the maximum you can send? See, the sender window cannot be the 0, 1, 2, 3. Right? Sender window cannot be 0, 1. Cannot be 0, 1, 2, 3, cannot be 0, 1, 2, but it can be 0, 1. So what is the maximum? Okay. See here. Suppose you have the sequence numbers like this. Okay. I mean, like this, and keep on repeating. Can you send all of them at once? Just tell me. Can you send all of them at once? No, right? Because the duplicate sequence number should not be in the flight at once, right? No. Can you send this 0 to 10 at once? It seems that no. The reason is that whenever these all get accepted, receiver will be waiting for next 10. Okay. Okay. Let's suppose, I mean, just to make sure that I'm saying 10, not 11. I'm having 0 to 9. It doesn't matter, right? Okay. So whenever you are sending this 0 to 9, receiver will be accepting it, but because of all ACKs are lost, receiver is waiting for next 10 packets, and your retransmission will be this. It is coinciding with the receiver next 10 packets, right? So you will be retransmitting this, receiver will be waiting for this. So this is coinciding. Okay. Now tell me, can you send can you send, just let's suppose if I ask you, can you send 0, 1, 2? Can you send 0, 1, 2? If you send this, what receiver will be waiting for next? 3, 4, 5. And if you retransmit 0, 1, 2, this 0, 1, 2, is this coinciding with the receiver next expectations? Even if all of this lost, then the receiver will be waiting for 3, 4, 5, right? Even if all of this lost, which means you are sending 0, 1, 2, even if ACK for 0, ACK for 1, ACK for 2, even if all of this is lost, okay, receiver is waiting for 3, 4, 5, you are sending again 0, 1, 2, there is not a problem, right? 0, 1, 2, you can definitely send. It seems like 0, 1, 2 is fine. But what is the maximum? Can you send 0, 1, 2, 3? Can you send 0, 1, 2, 3? See, this 0, 1, 2, 3, is this coinciding? Is this coinciding with the next receiver expectation? Next receiver will be expecting these 4 packets. No, right? So you can definitely send 0, 1, 2, 3. Can you send 0, 1, 2, 3, 4? Receiver will be expecting this next, right? These 5 packets. You can definitely send. Can you send 0, 1, 2, 3, 4, 5? Can you send 0, 1, 2, 3, 4, 5? No, because receiver will be expecting these and next packet, and this 0 and this 0 is coinciding. So what is the problem here? The problem is that, see, if you are sending, okay, let me just tell you the problem with this. If you are sending this 0, 1, 2, 3, 4, 5 at once, okay, just a second, just to make sure that your annotated notes look nice, okay. I mean, you understand just from the annotated notes. So what I'm saying here, that even if you're sending 0, 1, 2, 3, I mean, okay, you are sending 0, 1, 2, 3, 4, 5. If all ACKs are lost here, okay, ACK 0, ACK 1, if all of these ACK get lost here, then receiver will be waiting for 6, 7, 8, 9, 0, right? Receiver will be waiting for next of these 5. And you are retransmitting 0 also. Receiver will think that, okay, this 0 and this 0 is same, right? It will accept it. Are you getting my point? So that's why if receiver is waiting for something next, that should not coincide with whatever you are retransmitting. Okay. So this is not possible. Okay. Not possible to send. So what is the maximum you got here? I think till 5 till 4 it is working, right? Till 4 it is working. So 0 to 4 it was working, right? Because in that case the next 5 receiver is waiting for this, which is not coinciding. Okay. So if you are having any sequence numbers, let's suppose you are having sequence number anything starting from 1, starting from 0, doesn't matter. Let's suppose starting from 1, I can start from 0 also, but for this example, let's say I'm starting from 1. Let's suppose you are having till 100. Okay, till 100. Can you tell me? Can you send? Okay, this will be repeating. I mean, 1, 2, 3, 100. This will be repeating. Can you send all of this 200 packet at once? Definitely not, right? Can you send this 100 packet also at once? The answer is no, because if all of the ACK is lost, receiver will be waiting for this, and the retransmission is basically coinciding. Now, what is the maximum window size you can send? You can send till 50, right? You can send till 50, because the moment you send 50, receiver will be waiting for next this packet, which is not coinciding with your retransmission. So whatever you are sending, maximum could be the sequence number divided by 2. Your window can have 50 packets. If your sequence number is still 100, if your, I mean, we call it available sequence numbers. How much available sequence numbers you have? Sequence number is 100, right? If your available sequence number, I'm just calling it ASN, okay, available sequence number. If your available sequence number is still 100, you can send 50 packets only, right? I mean, even if you send 51, is there any problem? If you send 51 at once? Yes. What is the problem? That receiver will be waiting for till 1 next. So this 1, which is the next packet, and this one is which is retransmission, will coincide. So can you send till 51? Then answer is no. Can you send till 50? Yes, because receiver will be waiting for, see, this sequence number should be divided by 2. I mean, if you are having 100, it should be divided by 2. This part is given to the sender. Okay, now receiver will be waiting for the next distinct set of sequence numbers. This is necessary. Okay, next completely distinct set of sequence numbers than this. So that is why this sequence number should be divided by 2. I will say that, okay, sender will be sending this and receiver will be basically waiting for this. Receiver will be waiting for this. Okay. Is this fine to everyone? So I can say sender can send at most this and receiver will be waiting for next this. Okay. Should I make it a little more interesting or should I first make sure that you understand this? Have you understood this? Can I play with the words now? Okay. Now you just tell me, suppose the sender is sending 50 packets. Here the receiver was also waiting for 50 packets. But suppose somehow I am saying the receiver is not waiting for 50 packets. Receiver window size is different than sender window size. And I'm saying the receiver window size is just, let's suppose, 10 packets. Then can sender send more than 50? If receiver is just waiting for 10 packets, then can sender send, let's suppose this is 60. Can sender send till 60? What do you think? Here in this case, yes, because the next packet, the next 10 packets it will be waiting for from 61 to 70. These are the next 10 packets that receiver is waiting for, which is not coinciding with your current sequence numbers, right? So you can definitely send till 60. So what is the maximum limit you can send if receiver is just waiting for 10 packets? If receiver window size is just 10 packets, what is the maximum limit you can send? Don't worry. I mean, even if you are sending, even if it is go back and you are, I mean, don't worry that, okay, how you can send 60 packets if receiver is just waiting for 10 packets. It means that receiver can buffer 10 packets at once. Okay. Which means one will arrive, then receiver will say that, okay, now I'm waiting for, I mean, it will keep on sliding. I mean, in go back and we just have one window, right? One window for the receiver. Okay. So maximum you can send till 90 here. Why? Because if you send this, then even if all of this is lost, receiver will be waiting for the next sequence number receiver will be waiting for this, which is not coinciding with your current sequence numbers, right? So whatever is given to receiver, I mean, what is receiver going to expect next? I mean, which will be WR, which is the window size of the receiver. And whatever the sender is sending should be total, the sender window size, whatever sender is sending, whatever the receiver might expect next, should be definitely less than equal to whatever is the total, or maybe here, let me just call it, it should be equal to 100, right? For now, let me just call it equal, which means whatever you are sending, whatever receiver may expect next, which is the 10 packets, it should not, I mean, this should be the 100. You give it anything. If you are saying that, okay, you want to send 95, then receiver window size cannot be more than 5. So basically the sequence number should be given, some part of it should be given to the sender, some part of it should be given to the receiver. It cannot be the case that, okay, you cannot send, I mean, the packets that you are sending, the window size of the sender and receiver cannot be greater than 100. Okay, which means combinedly it cannot be greater than 100. Which means if you are sending 100 packets, let's suppose you are sending 100 packets at once, 1 to 100. Okay, it will be a problem. Why? If you are sending 100 packets at once and then 1 to 100, then what is the sender window size? 100. Let's suppose receiver window size is also 100. What is summation of these two? 200. Is this lesser than what is the available sequence number? It should be strictly lesser than that. Since it is not lesser than, so that is why it is not possible. So you can't send 100 packets. Basically, if you have 100 sequence numbers, you can divide in any way, but some part of it is given to sender, some part of it is given to receiver. You can divide in any way. Understood? So whatever the sequence numbers that you have, right? Whatever the sequence numbers you have, okay, available sequence numbers, right? Sequence numbers means you can the numbering you can start from anywhere, 300 to, let's suppose, 400. So, or maybe 399. Okay. So how many available sequence numbers? You can numbering you can start from anywhere. It is 100 available sequence number, right? 100 is available sequence numbers. So tell me, is this possible to have the receiver window size? Which of the following is possible? To have sender window size as 50, receiver window size also as 50. Is this possible? Sender window size as 70, receiver window size as 70. Is this possible? Sender window size as 30, receiver window size as 30. Is this possible? Sender window size as 100, receiver window size as 100. Which of the following is possible? If I say A, B, C, D. See, these are the 100 sequence numbers. You can divide in any way. I mean, you give 50 to sender, 50 to receiver, that's fine. So A is possible. You give 70 to that, now you just left with 30, right? You can't give 70 to receiver also. So there will be coincide. 30, 30 definitely possible, 100, 100 not possible. So that is why A and C are the answers, right? Numbering can be start from anywhere. Don't worry about this numbering. Okay, I'm just telling you the available total sequence number space. You have 100 sequence number, 100 distinct sequence numbers. Okay, numbering you can start with 0, you can start with 1, you can start with 300, you can start with 500, you can start with 123, you can start with 33, you can start with anywhere. Numbering you can start anywhere, right? So I can say this available sequence number, yes, available sequence number, and this window size of sender and window size of receiver should be less than or equal to available sequence number. It can be equal also, okay? Yes. So this is the final relationship we have got. As long as this is there, we are fine. If this is not followed, which means the available sequence number should be divided into sender and receiver. Okay? You can't have the overlap. If this is not followed, you will be having the overlap. And the overlap might create the problem if the all ACKs are lost. Okay. Understood? Now, even if this is, this is true for any either selective repeat or go backend. Even if this is go backend, in go backend, the receiver window size is fixed, right? Can you tell me what is the receiver window size? 1. Okay. So suppose you have 1 to 100. Can the sender be containing all 100? If the sender is containing all 100, then the window size will be 100, right? Let's suppose the available sequence numbers are 100. Available sequence number means what? The distinct sequence number that I have here, right, are the 100 sequence numbers. Okay. Now, can the sender window be containing 100? Can you send all of the 100 at once? What is the problem? If all ACKs are lost, then receiver will say, okay, 1 got, 2 got, 100 got. Now, what is the next packet the receiver is expecting? If all 100 has been received, acknowledged, but what is the next packet then receiver will be accepting in that case? Packet number 1, right? Receiver is waiting for packet number 1. Now, at your retransmit, whenever you retransmit this one, receiver will think that, oh, this is the new packet, right? So this retransmission of the packets and the whatever receiver is waiting should not collide. So basically, this formula which I said, WS plus WR, this should be less than or equal to available sequence number. Whatever you have, go back and select repeat or any protocol, this formula should be followed. Okay. So what is the maximum size of sender window in go backend? Answer is, yeah, n must be 99, right? 99. So n is 99. Yeah. Okay. So this is n. That's what we say in go back n. Go back here, n is the sender window size. Okay. Understood? Cool. Yeah, total -1. Basically here the sender plus receiver should be less than or equal to available sequence number, right? So if this is 1, okay, so WS is less than or equal to, this is 100 minus 1, right? So WS can be anything from 1 to 99. So maximum could be 99, right? You can have 99. If you have available sequence number as this, then maximum you can have 99 in the window. Okay. Anyway, this is the same thing that I have taken from Forogen. We don't need to look at it because we have already seen this. So what they are saying, if all ACKs are lost here, I think they have given a go back and if you have 0, 1, 2, 3 sequence number, can you send all of these 0, 1, 2, 3? If you have 4 sequence number, can you have 4 as a window size? The answer is no. Why? Because if you send all of them, if all ACKs are lost here, then whenever you are resending, can you tell me what receiver is waiting here? Receiver is waiting for 0. Whenever you're resending, this zero will be accepted wrongly, right? So that's what they are saying. Erroneously accepted and delivered as new data. Have you understood this particular diagram, this particular part of the diagram? And this is basically correct diagram where you are sending only 0, 1, 2. Now receiver is waiting for what? If all of this is got accepted, receiver is waiting for what? Can you tell me? 3, right? Receiver is waiting for 3, and your retransmission doesn't contain the 3. So this is fine. This I have taken from 4OGEN. Now let's just solve this question. This question is saying, consider selective repeat protocol studied in class. Okay. Suppose that the sequence numbers available are 0, 1, 2, 3, 4, 5, 6, and the window size used by the protocol is n equal to 4. Now, will the protocol will work properly in this case? What do you think? If the sequence numbers are this and you are sending 0, 1, 2, 3, 4, will the protocol work in this case? See, they are saying 0, 1, 2, 3, 4, 5, 6. If you are sending this 0, 1, 2, 3 at once, will it work? Just think about it. Easy question, is it? It will not work. Why? Because the receiver will be next waiting for 4, 5, 6, and 0. And your retransmission and the receiver is basically coinciding. And also you can see that, okay, available sequence number here is 7. Available sequence number is 7. In selective repeat, window size of the sender and the window size of receiver is same. So which means that window size of sender and window size of receiver, it should be less than or equal to available sequence number, but this 4 and 4 plus 8 is not less than or equal to 7. So that's why it will not work. Right? Okay, I hope you understood. So it will not work. Right? Why? Because this is coinciding, right? You are waiting for this and the retransmission, and this is coinciding. And also with the formula also, I hope that is okay. You just apply the formula. Okay. Let's just see this. Suppose that we run the sliding window algorithm, the sender window size is 6 and the receiver window size is 4, and assume that sequence numbers are 0 based. I mean, they're starting from 0. Okay. Okay. So find the smallest value for the maximum sequence number and to be used for the successful transmission via selective sliding window protocol. Find the smallest value for the maximum sequence number to be used for the success, which means they are saying that, okay, starting from 0, what should be the sender window size? I mean, from 0 to what number? They are saying if it is from 0 to n, then what is the value of n? If this is the sender window, then what is the value of n? See, suppose that they run sliding window protocol, sender window size is 6, right? Okay. And the receiver window size is 4. Okay, maximum available sequence number they're asking. Okay, so they're asking for the available sequence numbers, not the sender window size. So if the sender window size is 4, the receiver window size is 6 plus 4, basically available sequence numbers. The total number of sequence numbers should be, you can say greater than or equal to 10, right? So you can say 6 plus 4. It should be greater than or equal to 10. WS plus WR. So distinct sequence number should be greater than or equal to 10. So you must be having at least 10 sequence numbers to run this protocol. Okay. You must be having at least 10 sequence numbers. If you are starting from 0, then what is the maximum sequence number? What is the smallest value of the maximum sequence number? If you are starting from 0, 9, right? Okay. So 9 is the correct answer here. Understood? This 9. Okay. So I hope you got this question. So they are saying what is the maximum sequence number that you can use? What is the smallest value of the maximum sequence number? Anyway, so this is the 9 as an answer. What about this? give the example showing that n minus 1, which means whatever is your answer, which means 8, 0 to 8 won't suffice here. So can you give the example? Let's just give the example. Okay, they are saying if we are having the sequence numbers from 0 to 8, it won't suffice if the sender window size, is 6 and the receiver window size is 4, then these 9 sequence numbers alone won't suffice. Can you give the example? Yes. So you send 0 to 5. Okay, you send, the 6 packets you send 0, 1, 2, 3, 4, 5. And what receiver will be waiting for next? 6, 7, 8, and 0, because of the 4 window size. This is what receiver is waiting for next. Is this okay to everyone? So receiver will be waiting for this next, and let's suppose all ACKs are lost. Then your retransmission of 0 is coinciding with the receiver waiting for next. So that is a problem, right? Have you understood this example? Let me also read it out. So what they are saying, the sender first sends 6 frames 0 to 5. The receiver is expecting next 6 to 0. Since the sequence number wraps around, instead of 9, we have the sequence number 0. So we have the sequence number 0. After timeout, the sender sends the 0 to 4, 5 again. Okay, but if all ACKs are lost, then you have 0 to 4, 5 again. Receiver accepts this frame 0, but it was the old incarnation instead of the new frame sequence number 0. So basically they are saying if you are sending this 0, receiver will by mistake accept it. Understood this example? They are also saying the same thing that we are saying from the explanation of this particular topic. Okay. Understood this question? Should I move to the next question? Okay. So now let's just solve this question. Now, what they're saying, the sliding window protocol needs a sufficiently large window to avoid stop and wait. Okay, we have decided that we have the window size of 200 is needed for the given communication link, determine the number of bits in the sequence number. So if you have sender window size is 200, okay, then in go back and the receiver window, will be 1. In selective repeat, if the sender window size is 200, then the receiver window size is also 200, right? In selective repeat, the window size is same. In go back and this is the window size. Okay. Now they're saying how many sequence number, distinct sequence number you will be needing here. So what do you think? How many distinct sequence numbers you will be needing here? You will be needing 201 sequence numbers, right? You will be needing distinct 201 sequence numbers. Here you will be needing 400 sequence numbers. Is this okay to everyone? But they're asking, minimum 201 you will be needing. Okay. But they're asking that number of bits. If you want 201 sequence numbers, then how many number of bits will be required? If you want 8 sequence numbers, you need 3 bits. If you want, let's suppose 16 sequence numbers, you need 4 bits. If you want 32 sequence numbers, you need 5 bits, right? If you want 201 sequence numbers, then you need log of 201. So this is 2 power 6, 2 power 7, 2 power 7, right? 2 power 8. 2 power 7 is 128 only. 2 power 8, 8 bits can represent 201. 256 basically. 8 bits can represent 256. So I think 8 bits, minimum 8 bits you will be needing. Can 7 bits is fine? Can 7 bits is fine? 7 bits won't be able to represent this 201, right? Okay. So here you need 400 different sequence numbers. If you need 400 different sequence numbers, then I think 2 power 8 won't be doing. 2 power 9. 2 power 9 and 5 and 2, right? So 9 bits you will be needing here. You will need 9 bits here, you will need 8 bits here, right? At least 9 bits. Okay. Now let's just solve this question. Consider go back and suppose the size of the sequence number space, number of unique sequence numbers is n, and window size is n. Okay. So they are saying that number of unique sequence numbers is n, which means let's start from 1. It doesn't matter. Basically, see, if you want to have the unique sequence number, you can start from 1. If they are saying number of bits I mean, see, unique sequence numbers, you can start with any number. It doesn't matter. So why we start from 0? Why we start generally from 0? Because whenever we are having, let's suppose 3 bits, then you will be able to represent the 0, right? I mean, with 3 bits, you will be able to represent 0 to 7. So if you're saying your sequence number start from 1, then you're just wasting one of the sequence number, basically, right? I mean, you can represent 0, then why not to use this 0? Anyway, so if you want, you can always start from 0. So they're having 0 to, and I mean, these are the distinct sequence number that you have. If you are send, they're saying if you send all of them at once, which means window size is also the same, that go back and protocol will not work. So go back and will work or not here? No, right? Can you tell me the example? So if you, let's suppose, if you send this 0, 1, 2, let's suppose 7, okay, this is n is 8. I mean, let's suppose you're sending till 7. If all AC keys are lost, then receiver is again waiting for which one? 0. And your retransmission also contains which one? 0. So that's why it will not work, right? I mean, easy example we can give. So they've also given the same example. They have just taken n equal to 2. Anyway, it doesn't matter. So if you're sending 0 and 1, I mean, if you are having 2 sequence numbers are distinct, and if you're sending all of them at once, if all AC keys are lost, or maybe here they've considered only one of them as lost. I mean, even if all are lost, this is fine, okay? Even if all are lost, then you will be anyway sending 0 and 1. Okay, 0 and 1. This 0 is actually coinciding with your whatever receiver is expecting next, so that is a problem. Okay. So by the way, this example is just trying to show that even if all AC keys are not lost, okay, the common, okay, whatever is the common, okay, see, your retransmission contains what? I mean, you have just sent 0 and 1, right? You have 0 and 1. Receiver is waiting for next 0. Okay, whatever is common, even if just common ones are lost, okay, even if just common ones are lost, then also there is a problem. Even if one is not lost, even if this is not lost, even if the common ones are lost, then also there is a problem, right? Anyway, you can just consider that what if all are lost. Have you understood this? Okay, maybe you understood, right? Little bit. Great. Let's just solve this question. The maximum window size for the data transmission using the selective reject protocol with n bit frame sequence number is. What is the answer? Maximum window size in the, if there is an n with available sequence number, distinct sequence number, you can have 2 power n. And in the selective repeat or the selective reject, you need to divide by half and half. So which means you need to give half of them to the sender and half of them to the receiver. Okay, the window size they're asking. So 2 power n divided by 2, which is 2 power n minus 1. B is the answer, right? Okay, understood. Suppose the same question has been asked, but for go back n. In go back n, what we will do? It is 2 power n. If this is total, and then the sender window size will be the sender plus receiver is 1, right? It should be less than or equal to. So sender window size can be maximum 2 power n minus 1 in the base, not in the exponent, right? So then C will be the answer. If it is go back n, then C will be the answer. Okay, understood? See, if it is you have 2 power n available sequence numbers, right? Easy, very easy. If it is go back n, then WS plus WR is always 1 less than or equal to 2 power n. So what is WS? It could be maximum, it could be 2 power n minus 1 in the base. But here in the selective SR protocol, WS plus WR should be less than or equal to 2 power n. Here these two are equal. So 2 into WS is less than or equal to 2 power n. Here the WS is less than or equal to 2 power n minus 1. Okay. Hope you understood. So this minus 1 in the exponent here, minus 1 in the base here. I mean, you don't need to remember this. You just need to understand that in any case, WS plus WR should be less than or equal to. You need to divide the available sequence number into WS and WR. If you are having the extra sequence numbers, which means you are having 1 to 100, you don't want to divide all of them, that is fine. That is fine. I mean, the available sequence number can be greater than this WS plus WR, but it cannot be lesser than WS plus WR. Okay. Just let me know what is the answer here. In a sliding window ARQ scheme, the transmitter window size is n and the receiver window size is m. The minimum number of distinct sequence numbers required to ensure the correct operation of the ARQ. Receiver window size is m, right? So minimum you need m plus n sequence numbers. M plus n sequence numbers, right? So C is the answer. Should you be needing, let's suppose there is one of the option, okay, E. Should you be needing m plus n plus 1? Do you need this much minimum sequence number? What do you think? Will E be the answer or C be the answer? You don't need plus 1. Minimum you need m plus n only, right? Okay, whatever the sender, whatever the receiver, you just need to give them m and n. Yeah. Will this work? Yes, this will also work. It's not like it will not work, but it won't be minimum. Yes, right? Okay. By the way, this question was asked on the Stack Overflow also, that in selective repeat, why this is the case that window size must be less than or equal to the half of the size of the sequence number space in SR protocol. Why that is the case? That question got 28 upvotes to my surprise, which is like quite I mean, one of the things to ponder. Like, it is not easy easy to get 28 upvotes on the Stack Overflow, right? So that's why I just took it as a screenshot. They are also having a similar sort of explanation, right? I mean, they're saying that, okay, if you are sending 0, 1, 2, 0 is sent, 1 is sent, 2 is sent, they're saying, okay, 0, 1 and lost. I mean, anyway, you can read out this explanation. This is very easy to understand once you understand the whole lecture, right? This will be easy to understand. Now we want to solve more gate PYQs. Okay, so all of the PYQs I have taken here, which are related to stop and wait and selective repeat. So do you want to solve them now, or just take a break and then solve? So this is 1, 2, 4, 5, 6, 7, 8, 9, 10, 11. Yeah, 11 PYQs. Okay. So if you want, we can take a break of half an hour maybe, and then we can solve these 11 PYQs quickly, right? Okay. So thank you, everyone. Take care. Bye-bye.